This is the last 240 video I'm doing, and if you're watching this video, then hang in there. The semester is almost done because this is the last thing that this class covers. So welcome to chapter 9.10, section 10 of chapter 9. This is the last thing on nonlinear systems. And if you watched the previous video on linear systems, where I spent half the video just drawing stupid spirals, uh, again, you'll rarely have to draw on an exam. I can only think of one instance that this has ever happened. Same thing with nonlinear systems. These guys are a lot worse than those linear systems as well. So let's take a look then. So on page 657 in your book, we're anchored by this table again. Now, a quick heads up, don't get bamboozled by this table like I did, because what happens is, so you know how both tables start out with like eigenvalues, and then they tell you what like uh, the linear and the nonlinear systems are. So this table is better than the table on 651 because it includes both of them. But the table on 651, they swap like they like this pure imaginary guy is like up here. So it's in the middle. So if you copy down that table and you're just adding on to it, be very careful on what you copy for the nonlinear systems and make sure that purely imaginary goes with this stability indeterminate guy, which if you were like me, like a moron, and for recitation, I actually accidentally copied that purely imaginary was a stable spiral because I thought that it was still the third to last entry. Anyways, you guys probably want to see how to actually do these kinds of problems. So again, keep in mind that this table 9.10.1 is what we're going to refer to like all the time. And now we're talking about nonlinear systems. So what is a nonlinear system? You'll get something like this. You'll get a question like this. It's find and classify all the equilibrium points, or this might be like critical. I'm not sure what the book uses actually, of the system. And let's say I have dx dt, or like x prime is equal to y cubed minus y, and then dy dt, or y prime is equal to x squared minus x. So again, this could be written as like x prime is equal to, or y prime is equal to, depends on your professor's favorite method of notation. Anyways, so how do we find the equilibrium points of the system? This is it's kind of like math 114. So what happens is I have to find points where both these guys are 0. Both x prime and y prime are equal to 0. So what I have to do then is I have to say y cubed minus y is equal to 0, and x squared minus x is equal to 0. So how many of these points are there? Well, y cubed minus y is just y times y squared minus 1 is equal to 0. Yes, and then this guy is x times x minus 1 is equal to 0. So what can y be? Y can equal minus 1, 0, or 1, right? Because from here I get plus or minus 1, and then from this y on the outside I get 0. And then x can equal 0 or positive 1, okay? So I have 6 pairings of points that I need to check. So here are my critical points, or equilibrium points. I have negative 1 or 0, okay. So this is x and that's y. So I have 0, negative 1, 0, 0, 0, 1, okay. And now I have 1, negative 1, 1, 0, 1, positive 1, okay. And so these are the 6 equilibrium points that I need to find. So now what? Now, like, what am I supposed to do? Well, let's call these guys a different name again. Let's call this top guy F, and let's call this bottom guy G. So now so the second step after you find the equilibrium points, right? because we have to classify these guys, right? So we've done the find part. We need to classify them now. And if you remember how we classified equilibrium points for linear systems, we had some kind of matrix. And right now, there are no matrices to be seen. So in order to classify the equilibrium points, I got to find a Jacobian matrix. All right? And what is the Jacobian matrix? Well, there's a reason why I named these F and G, is because J at a point x comma y is equal to this matrix partial f partial x partial f partial y partial g partial x partial g partial y. Okay? And I have to evaluate this at every single point, but in general, I can figure out what this matrix is right now. So f, right, it was y cubed minus y. So the partial of that with respect to x is 0. And then y cubed minus y, the derivative is 3y squared minus 1. Okay? And then partial g partial x, well, okay, so g is x squared minus x at the way top right there. And now, so dg dx is 2x minus 1, and then dg dy, well, g, or this guy, has no y terms, and so this is 0. Okay, so that's how you create the Jacobian matrix. Now you got to evaluate it at points. So how do we evaluate at points? Okay, so I find j at 0, negative 1, which is then 0, 2, negative 1, 0. Okay, and what do I do now? Now I need to find the eigenvalues, right? Of course we're finding eigenvalues. And so what is this? Well, then the determinant of this guy becomes right, of this guy minus lambda I, negative lambda, negative 1, 2, which is lambda squared plus 2. And so lambda equals like plus or minus root 2 times I. Okay, and then what do I have? Then I need to go to my handy dandy textbook, and I have plus or minus root 2i. Okay, so it's purely imaginary, and so it's a center or a spiral point stability indeterminate. And which one do I know? So generally speaking, you can just cite this. I actually have no idea how to distinguish them, and so we'll just say that the center, this is a center or a spiral point. The stability is indeterminate, and I guess one way we can check it then is I might create a addendum. I might not. This really you really don't have to worry about these usually. So we'll just say it's a center or spiral point. Stability indeterminate. Okay, so this is a center spiral. This is a center or a spiral. Stability indeterminate. Okay, so that's only one of them. So now I got to do j of 0, 0, which is 0, negative 1, 0, negative 1, 0. Okay, so now this is the determinant of lambda, negative lambda, negative lambda, negative 1, which is equal to lambda squared minus 1. Okay, and so now lambda is equal to plus or minus 1. And now we go back to textbook. Lambda is equal to plus or minus 1. So that's opposite signs, and so we got a saddle. Okay, let's erase these guys. So we got a saddle for this guy. And then now what? So j is equal to, now j at 0, comma, positive 1 is actually the same matrix up here, all right, is the same as this first guy. These two have the same j's. And so this is also then a center or a spiral point. Okay, so this guy at 0, 1 is also a center or a spiral point. And then now we can find j of 1, comma, negative 1, which is 0, 3, so this is still 2, and then you got positive 1? Yeah, positive 1, 0. Okay, which means that the determinant is of negative lambda, 2, 1, is lambda squared minus 2. So lambda is equal to plus or minus root 2. And so these have opposite signs, so this is going to be a saddle. Okay, and then you got j at 1, 0, which is 0, negative 1, 1, 0. And now what? So now you got the determinant negative lambda, negative 1, 1, negative lambda. And this is lambda squared plus 1, and so lambda is equal to plus or minus I. So again, this is going to be a center or a spiral point. The stability is center or spiral stability indeterminate. Okay? And let's see. Last point is lambda at 1 comma positive 1. All right? And I get 0, 2, 1, 0, which is the same thing as this guy up here. And so I'll get then another saddle point. All right, so these two guys also share the same j's. So why is that lambda? So at the point 1 comma 1, this is also a saddle point. And yeah, so now we've characterized all 6. We've characterized all 6 points, all 6 of them, and you're done. So you've characterized the equilibrium points, you've found them, and so now what? So one of the questions that students like to ask is, how do we know we're done with finding equilibrium points? And that's just something you have to practice. It's like finding the critical points. Remember in Math 114, when you have like local mins and maxes, you have to find the critical points by taking derivatives. That's almost analogous to what we're doing right now. It's very similar. And yeah, even then you didn't know when you're done. You just had to, you had to check all the cases and be confident that, right, y has 3, x has 2, so y has 3 choices, x has 2 choices in this case, which means that I have 6 points I have to check. So, alrighty, we've characterized all these equilibrium points. I want to say, I'm not going to be 100%, I'm not going to be 100% like, yeah, I don't want to say this is 100% true. I know this fact is true. If the trace is 0, so for this this point right here, the center or this point right here where it's a center or a spiral, but we can't determine what it is. If the trace of the matrix is 0 and the determinant is positive, then it's a center. Okay, so I know that much is true. So this guy is actually going to be a center right here because the trace is 0, the determinant is greater than 0. Same with this guy. This guy is also a center. And this down here is, this point right here is also going to be a center because the trace is 0 and the determinant is 1. Okay. I'm not actually sure about the other conditions. So if I ever figure that out, if I figure that out, I'll talk about it in my class. But this is, again, you can probably just leave it as center or spiral stability indeterminate. So that's it for Math 240. We're done. This is the last video, and thank you for sticking around. If you have any questions, I have my website link at the bottom of all my videos. This is a really enjoyable class to TA. I actually was really surprised at how much I enjoy TAing this class, being like a 114 try hard TA. So yeah, again, thanks for watching all these videos. If you slog through all 50, kudos to you. I know a lot of you guys don't go to class, so you guys, the videos might just be your only way of catching up on the material. And unfortunately, this is the Plug and Chug series, so not much theory was covered. You need to know theory for this class. And otherwise, yeah, thanks for watching. Good luck on your exams. If you're watching this video, probably near the final, good luck on your final. And I will catch you guys in another video if you're going to watch any more of mine.